In this presentation, we will be exploring more on the concept of conditional probability. A summary of the different scenarios for probabilistic events will also be presented towards the end of the video. So conditional probabilities work in scenarios when the probability that an event may happen is dependent on the occurrence of another event. Recall that there are two ways by which we may interpret the conditional probability of, say, event B. We can say the probability of B given A is true, or the probability of B given A is not true. So notice in these examples how event B's occurrence is dependent on whether event A happens or not. Now, the sum of the probabilities of B happening both in the presence or absence of event A is called its unconditional probability. So, unconditional probability is simply symbolized in this example as PRB. So, this is the unconditional probability of B. So, how are these two related? You can see in this equation how the unconditional probability of B is just a sum of the conditional probability of B given A is true and the conditional probability of B given A is not true. So in the next slide, we will see how this equation is derived, especially that we have these additional stuff here going on. So first, if you're going to think about unconditional probability of B, you will come up with the idea that this is the probability that B happens and A is true, plus the probability that B happened and A is not true, right? Because it's unconditional probability of B. Okay, so B occurs with or without A happening. Now, these two parts of the right side of the equation may actually be fleshed out in these two equations. So notice here on the first one, we have an equation and it looks familiar. It looks familiar because it's actually from the conditional probability equation. Do you still remember that? The probability of B given A is equal to the probability of B and A happening divided by the probability of A. If we just cross multiply this, we get this right portion of the equation. And if we cross multiply this with a 1 here, we get this left side of the equation. The same is true for this third equation that you see here. The only difference is instead of considering A happening, here we have A not happening, the complement of A. So these are all from the conditional probability formulas. So all in all, if we are going to consider unconditional probability of B, then we have to add both of those conditions. And you see how we arrive with the original equation. So this is a summary of what unconditional probability is. So it says here that the unconditional probability of B is the weighted average of the probabilities of B occurring in two mutually exclusive events. Okay? The first one is when A is true, and the second one is when A is not true. And the weights are, of course, the probabilities of both A being true or A not being true. So in this example, we are going to apply that particular equation. Okay? So suppose that we have 100,000 women with negative mammograms. Okay? And 20 out of those 100,000 will be diagnosed with breast cancer within 2 years. Okay? So as you can see here, the probability that B happens given that A is not true or that the mammogram is negative is 0.0002. And then, 1 woman in 10 with positive mammograms will be diagnosed with breast cancer within the next 2 years. Or, PRB, the probability of having a breast cancer when the mammogram is positive is 0.1. Okay? So, let's say that that's the background. And suppose that 7% of the general population of women will have a positive mammogram. The question now is, what is the probability of developing breast cancer over the next 2 years in this general population? Okay, in this general population. So, we are talking here about the unconditional probability of the general population. So that's the PRB of the general population. Okay. So the probability of the general population will be of having a breast cancer, the general population will be equal to, first, the probability of having breast cancer when the mammogram is positive times the probability when the mammogram is positive. Right? That's from the unconditional probability equation. Plus the probability of having breast cancer when the mammogram is negative times the probability of the mammogram being negative. Okay, so we just have to provide the numbers here. What's the probability of having breast cancer when the mammogram is positive? That's already given, and that's 0.1. And that's times. What's the probability of the mammogram being positive? Is it given in our problem? If you read again the second paragraph, it is. It says here, suppose that 7% of the general population of women will have a positive mammogram. So therefore, this probability of having a positive mammogram is 7% or 0.07. Plus, what's the probability of having breast cancer when the mammogram is negative? Well, that's given here. That's 0.0002 times. What's the probability of the mammogram being negative? Well, that's simply saying as the mammogram, as the probability that remains after the mammogram has become positive. So the probability of the mammogram being negative is just 1 minus 0.07. Or, this is 0.93. So if we multiply these, and then add both, we are going to arrive with an answer of 0.00719. Or, that's 719 women for every 100,000 women. So that's the probability of developing breast cancer over the next 2 years in the general population. 719 women out of 100,000 women. So let me just erase this. So you see, this is the formula that we used, okay? And we may actually, the unconditional probability equation may actually be summarized by the total probability rule. So this is the total probability rule. Notice here how the conditional probability is multiplied with the probability of the previous event, just like what we're doing here, times probability of A. But then here, the limit is K, right? So that's why we have a summation sign, because we're just going to add each one of them until we reach K. Here's another example. So, suppose we are planning a 5-year study of cataract in a population of 5,000 people, 60 years old of age and older. We know from census data that 45% of this population, okay, let's just write that one here. 45% of the population is from 60 to 64 years old. Okay. And then 28% of the population are from 65 to 69 years old. And 20% of the population are from 70 to 74 years old. And 7% of the population are 75 or older. Okay, sorry, it's quite messed up. Suppose we know from a study that 2.4%, 4.6%, 8.8%, and 15.3% of the people in these respective age groups will develop cataract over the next 5 years. Okay, so how are we going to work on this? Okay. Well, first of all, let me just transfer the 45% here at the bottom. Okay, so we know from the second statement that we read here that 2.4% of the first age group, the 45% age group, will develop cataract in the next 4 years. And I transfer that here at the bottom, so I'm going to write here at the bottom, 2.4% of this age group will get cataract. Cataract. And then 4.6% of the next group will get cataract in the next 5 years. So that's the one here on top. And then 8.8% of the next group. And then 15.3% in the last group will get cataract in the next 5 years. Okay? So the question is, what percentage of the population in our study will develop cataract over the next 5 years? And how many people with cataract does this percentage represent? So what's going to happen is, you will arrive with a long equation that might look like this. The probability of having cataract in the general population. So, first we have our 45% of the first age group. And then there's a times 2.4% chance getting a cataract in that group. So, you might have this plus. In the second age group, the one here on top, that's 28% of the population, at least in the sample, times, that's a 4.6% or 0.046 plus in our third age group, there's 20% of them. It's 0.2 times the probability of getting cataract is 8.8%. And then plus, in the last age group, the one here, there's 7% of them in our sample. And the probability of getting cataract in that age group is 15.3%. So if we're going to add all of these, multiply and add all of these, if you have your calculators, we're going to arrive at a number 0.052 or 5.2% of the general population. Now, how many people are those? Is that if there are 5,000 that we started with? So we simply have to get 5.2% of 5,000. And that's equal to 260 people expected to have cataract within the next 5 years. So hints of conditional probability may be seen in this generalized multiplication law of probability. So this is generalized multiplication law of probability. If events A sub 1 up to A sub k are arbitrary set of events, then the probability of A sub 1 and A sub 2 and A sub 3 until and A sub k will happen will be equal to, first, the probability of A sub 1 times the probability of A sub 2 given A sub 1 happened, times the probability of A sub 3 and A sub 2. Sorry, the probability of A sub 3 given that A sub 2 happened and A sub 1 until such a time we reach this. The probability of A sub k happened given A sub k minus 1 happened. And all of these A subs up to A sub 1 happened. Okay, so don't worry, I don't think we're going to be using this formula often. Instead, let's just dwell on this last slide on the summary of the or and rules of probability. Okay, so first we have the event A or B, the or event. We also know this as the addition rule of probability. And then we have the and event or the multiplication law of probability. So for the addition law of probability, there are two scenarios, if they're mutually exclusive or not. If the two events are mutually exclusive, then this is how you get the probability of the two events. You simply add them. But if they are not mutually exclusive, there are two possible ways. But before that, let's look at this events A and B. If events A and B are mutually exclusive, is it possible for them to happen at the same time if they are mutually exclusive? Like heads and tails when you flip a coin, is that possible? The answer is no. So that's a null set, an empty set, 0 probability. While if they're non-mutually exclusive events, if they're independent or dependent or conditional, then you have this for the or rule or the addition rule. Okay? You need to subtract the part wherein both of them may happen at the same time. And that's the formula here. Now, in dependent or conditional probabilities, as we just talked about extensively a while ago, this is the formula. And to go back to the or rule, that's what you have to subtract from what you just added. So this is a summary of the different probability events and the rules that govern each of them.